I'm Juan and I'm going to talk about my Bright Sparks entry for 2012. Being a filmmaker, I spend a lot of time filmmaking with these DSLR film cameras. Now, the good thing about DSLRs is that they have large sensors and you're able to use cinema lenses. This allows you to get low depth of field and very cinematic shots. However, the problem that this creates is that because the depth of field is so low, it's very difficult to keep the subject in focus all the time, especially if the subject is moving closer or further away from the lens. This got me thinking about a need, and then I thought about a solution to this need. This led me to create a digital pull focus unit. Now what this unit allows you to do is remotely control the focus of the camera. So this means that a camera can be mounted to, say, a jib arm, camera tracks or Steadicam without the camera operator needing to be physically able to reach the camera himself. The unit is comprised of three components. Firstly, there's the remote control car remote. Now, in early prototypes, I used only this lever to control the focus. However, this didn't allow a very great degree of control. So, for this version, I used an external potentiometer connected to a voltmeter. Now, as I rotate this wheel, the resistance value of the potentiometer changes, and in turn, the potential difference across the terminals of the potentiometer also change, giving different voltage readings. Now, for every resistance created by this potentiometer, this servo goes to a corresponding distance position. Then, what can be drawn from this is that for every resistance level, there is also a corresponding voltage, and hence, for every voltage, there is a corresponding focus distance. Because the potentiometer is geared down 1 to 40, I can do very many rotations of this wheel to do very fine increments of focus on the focus wheel. So as you can see, as I'm turning here, this focus ring is turning. This pull focus unit has come a long way. The first prototype used only friction, rubber on rubber, to change the focus. The second prototype used my mum's breed maker belt to change the focus. This third prototype uses a 3D printed gear suit.
I'm Nathaniel. I designed, 3D modelled and oversaw the 3D printing of the gears for the focus system. I modelled the gears in Blender, an open source 3D program, which allowed me to get the correct shape for the teeth and the scale of them on both of the gears and see how they would each function as physical 3D objects. The fact that we were using 3D printing to create these gears meant we were able to use precise measurements for everything and make them fit exactly to our system.
Another issue that we had in some of our earlier prototypes was the fact that the servo was analog. The way that I overcame this issue was that I bought a small digital servo, and then I took out the analog circuitry of this winch servo, which allowed for multiple rotation, and the digital component of the digital servo, and soldered them together. What this allowed me is to get a servo that had high torque and could do multiple rotations while having the precision of the digital circuitry. The reason why the digital servos work so much better is that their dead band width is so much smaller, which eliminates a lot of the creep and inaccuracy, and also their hold power is up to 10 times more than the analog servos. Now the magic of this unit is that I don't physically need to ever check the focus on the camera. All that I need to know is the distance that the subject is away from the camera, and then I'm able to find the corresponding voltage value off my voltage graph and set the focus blindly. So to illustrate exactly how this works, I will show you a test shot. Now here I am at exactly 1 meter away from the camera. Now, referring to my voltage distance graph, I know that the voltage that corresponds to 1 meter is 1.6 volts. Now to illustrate how this works, if I were to wind backwards, everything would go completely out of focus. But now I can find this focus mark again by simply going to that corresponding value. And here we are, exactly in focus at approximately 1.6 volts. I'm now going to move back to a mark at 3 meters. I know that at 3 meters, my voltage needs to read 2.17. you'll see me coming into focus. And there I am, completely without reference. Focus pulls can also be attempted with the subject in motion, as a continual refocus can be performed. Just to check. Here I am again in focus. One of the key issues we faced for the robotic head was finding a way of electronically controlling the speed of the pan and tilt components. The way that we achieved this is using a servo, or what was once a servo, taking out all the gears, unsoldering the motor. So what I'm now going to do is I'm going to solder on these two wires into these 2 points that the motor used to be connected to. Now the way that this works is because there are no gears connected to the potentiometer anymore, it will always stay at the central position. What this does is effectively turns the servo into a speed controller, outputting the voltage through these two cables connected to the terminals of where the motor was once connected. Now, as I was saying earlier, one of the reasons why we built the pull focus rig was so that we could mount the camera on our jib arm while keeping the shot in focus. Obviously the camera is going to be out of reach. So today we don't actually have the DSLR, but I'll still demonstrate how our robotic head works with one of our other handycams. Now the way that this works is I have the same transmitter as what we use for the pull focus system. Now as you'll notice, the pull focus control unit isn't connected, but what this allows us to do is that the pull focus is operated by one person and then another person is able to operate the robotic head. Now, as I move this joystick up and down, the camera will tilt, and left and right, it will pan. Now the way that I've constructed this is using 2 gear sets, here and here. Now these are 3-volt motors that are geared down 1,300 times. This gives the system very high torque, but also makes the motion very smooth and slow. These motors are connected to servos, as I showed beforehand, that have been butchered so that the potentiometer doesn't rotate. The servo then acts as a speed controller. The servos connect to a receiver and the receiver to a battery pack, so that when I control it from here, the system is able to be controlled. We laid these shafts down to the perfect size to fit inside of skateboard bearings to make sure that it was perfectly smooth. Now the jib arm itself was constructed by Robin and I in the school metal workshop over a period of about 6 months. Now what I'm going to do now is give you an actual demonstration of the system in action. For some of the films that we've done, we've mounted the 7.5 metre jib on top of our trailer, driven it down the road, and then got epic tracking and rising shots. This unit is still very much in the prototype stage, and there are many modifications and improvements that I'd like to do in the future. The end goal of this unit is that you can have it wirelessly connected to something like an iPad or a laptop, and you can just click on the area that you want to focus on and it will instantly focus on that area. The key difference between my unit and other already existing autofocus units would be that my unit would be depth-based, whereas the currently existing units are edge sharpness-based. The way that handycams focus at the moment is that they constantly move forward and past an image and find the point at which it is most sharpest. However, the issue with this on large frame sensors like these cameras is that the depth of field is simply too much to use this in production. The way that my unit would work is that it would have a depth camera connected to the camera itself. Now this could be a Connect, LiDAR, or any other system that can continuously measure depth. Just for example, the Connect can connect to a computer and output a luminance-based depth map. Now what I mean by that is that each pixel on the image that the Connect outputs has a corresponding depth value based on the brightness of that pixel. So from this what I can draw is that luminance has a relationship to distance. Now as explained earlier, this system here, the voltage had a relationship to distance. So if luminance has a relationship to distance and voltage has a relationship to distance, then voltage must have a relationship to luminance. The end product would be a program that can relate these two relationships and then output that voltage so that the remote can output that signal to the servo. This product could potentially revolutionize the film industry. Even in high budget productions, pull focus is still done manually, which is a very error-ridden method. This method that I suggest would allow a way of achieving accurate pull focus all the time without any mistakes. This could save millions of dollars in production loss based on shots that end up out of focus. So thank you for taking the time to look at my Bright Sparks application for 2012.